right? So okay, what's so that's the big picture plan. So okay, let's do part one, and then I start with lambda calculus. Okay, so what's lambda calculus? Basically, it's big disclaimer before we begin this. I'm not a mathematician. I will likely say silly things that are not correct. If you know that I'm wrong, then correct me in chat. My understanding is mostly, so I might be wrong in the pure mathematical sense about some of these things, but I'm more interested from the computer science / functional programming perspective. I'll try to be as precise as I can, but since I don't have I don't have a PhD in math now, not at the moment. We do have a math PhD in the family, but I don't think that translates to me having one. So yeah. Right, so let's see. Actually, I mean here, okay. Wait, don't you all have? How else do you do FP? Okay, so, okay, let's go back to where we're going. Okay, so lambda calculus is a framework in which we can basically talk about computation. That's the most important thing, right? So this was hello Joanna, thank you very much for following. Welcome to the stream. Told you before, head versus wall. Right, so let's see. So this was basically invented in the 1930s, and basically before the 1930s there were no framework on how to do computation, no formal framework, right? People just didn't know how to talk about computation in a mathematically formal way. And then some big, very, very well-known logician called Hilbert, like in the early 1900s, posed a bunch of like open questions, and basically one of them was, hey, let's figure out how to talk about computation, right? About algorithms, about writing a step of a series of algorithmic steps, or like a way to solve problems in a rigorous, formal mathematical way. So basically, within a couple of years of each other, Alonzo Church, Alan Turing, and Gödel basically all invented their own versions of solutions to this, and it was later proven that all of them were identical, or not identical, but equivalent to each other. The one we care about, and probably the most famous one, is Alan Turing's Turing machines, which I mean, sorry?
Was used during the war.
So I think that's the Enigma machine, which is something different. Yeah. But like the Turing machine is the framework that he invented for computation, and that was he was actually Alonzo Church's student after that, and they worked together a lot. But Turing's machine is very, very close to machine low level. It's about a moving left and moving right and writing variables and then reading later, and it's a very mechanical and impure way to think about algorithms, and it's very complicated to write algorithms like that, but it works, right? And modern computers are based on that somewhat, and it was easy to use the Turing machine's idea to create computations and to create the early assembly languages and computers and so on. But as people started working with computers, they realized that they can't use something like that because it's very hard to write programs in that, so they with more elaborate languages. Whereas lambda calculus is something that's more pure, more mathematical, more it doesn't it's a simpler and more, I think, a more elegant way, but it wasn't very good in the you can always say a joke, right, Vince? I can just don't worry about that. We can also have fun learning, right? So anyway, what is lambda calculus, right? So the main idea is that so let's see, first of all, it's a language, right? So let's see how we can construct this language. And there's this specific notation, which I'll write right now, which is something like and let me know if you've ever seen this sort of notation before, and if not, it's really absolutely no problem. So let's see. So let's say, first of all, it's a language, right? So let's see how we can construct this language. And there's this specific notation, which I'll write right now, which is something like and let me know if you've ever seen this sort of notation before, and if not, it's really absolutely no problem. So let's say Okay, so does this sort of notation look familiar to you in any way?
No.
Okay, cool. Absolutely no problem. Right. So what does this mean, right? So first of all, we are talking about expressions here, right? So we'll say that in order to create a lambda calculus expression, right, a term, a unit, right, something in lambda calculus, there are three ways to create it, right? And they are separated by this pipe operator here, right? So the first way is just to type like something like x or so let's write it in a different way, and then we will remember this as a notation because we will use it maybe sometime later, right? So let's see, in order to create a lambda term or expression, we could also call it, we can use write a variable name and we'll usually use x, y, z for this, right? Okay, write a lambda abstraction like lambda x.e. Okay, so what does this mean? Did I mistype?
Variable.
Okay, cool. Thank you. Right, so okay, we can write a variable, right? So for example, so let's see, this is 1, right? And this is 2. Let's not look at 2 right now. So if we use 1, we can, this is an expression, this is an expression, and this is an expression, right? So these are all correct expressions, and they're absolutely useless. They don't do anything, right? But they exist as expressions, okay?
Yeah.
Okay, so then we have this thing, right? Which is, so this sign, it's usually, this is lambda, the Greek letter lambda, but we'll use just backspace because it's harder to type in a file, right? So
makes sense.
Yeah,
Yes.
just think of this as lambda, right? But it's just a backspace when you type it. And then we have an x here, which is a name for a variable again, but it's kind of different than this, and we'll see exactly how later. And then what does it mean to type e here? Well, it means that here we can write any other expression that we've already defined, right? So it's kind of a way to define recursive expressions, right? Like when you so let's look at an example here, right? So these are all created with only using rule 1, right? So this is rule 1, right? And all of and below again, rule 1, right? So then if we use the rule 2, we can do lambda x dot, and then we can, instead of this e, we can use rule 1, right? Because rule 1 also creates things like e, right? So we can write, for example, this. Does that make sense?
Yeah.
Okay, so then we could also write this, right? Because rule 1 doesn't say that it has to be x, it has to be anything. Like it could be anything. But then, for example, we could do this, and then we can use rule 2 again. So we could do lambda y and then x, for example. Does that still make sense? And then the parentheses, you put it like this, right? Right, and we can go as, we could do this forever, right? Y, z, and so on, right? But at some point we need to stop and write something down, right? Cool, so this is like rule 2 plus 1 basically, right? And we apply a rule 2 a few times, as many times as we want, and then we finish up with rule 1. Okay, cool. And then we have one more rule, which is kind of like we put two expressions next to each other, right? This is what this means, right? So 3, we'll write a lambda, and this is called application by just... I hope that's how you type that word.
Yes.
Okay, cool. So it's something like, for example, XX would be one example of that, right? Because we use rule 3 plus rule 1 twice, right? Like we take two variables and we put them next to each other. And then we could do it as many times as we want, right? Because we can apply rule 3 so, for example, right? Does this make sense still?
Yeah.
Okay, cool. But then we could also do full Lisp, yeah. And just adding parentheses, but they're not really required. They have a logical way of evaluation in Lambda calculus, which we'll talk about. But for now, we're not worrying about that, right? And then we have what else could do? Well, we could do write a lambda here, and then put something next to it like y, right?
Okay.
So basically this is the short notation for explaining this thing, right? That's the whole idea. But it's like, if you know this, then it's easier to explain than this, right? Than writing everything down. Okay, cool. And I think we'll use this in the future, so that's why I wanted to introduce it now.